Walk down any grocery store aisle today, and you will see a massive demand for processed foods carrying specific biological health claims. For decades, the food industry relied on a simple formula to meet this demand. Isolate an active compound from a plant, extract it, stir it into a conventional food matrix, and label the result a superfood. The metric used to justify these claims was the ORAC score, the oxygen radical absorbance capacity. It served as the industry gold standard for quantifying exactly how well a chemical compound neutralized free radicals in a beaker. In 2012, the United States Department of Agriculture stepped in and pulled the plug. They formally retracted the entire ORAC database. The agency stated clearly that a high chemical bioactivity score, measured in vitro, has zero physiological relevance once that compound actually enters a human body. The chemical assays relied heavily on simple single-electron transfer models. These controlled tests failed to account for the harsh realities of human digestion, enzymatic degradation, and cellular absorption. Dumping reactive chemicals into a food matrix creates a marketing illusion of health. It does not create a genuine functional food. The concept of functional foods actually began in Japan in the 1980s as a regulatory category for specific health-promoting products. Despite decades of global expansion, the definition remains highly contested. In many jurisdictions, the term lacks a clear statutory framework, allowing standard nutrition products to blur the lines of medicinal claims. Modern regulatory bodies, like the FDA and EFSA, attempt to enforce strict oversight to separate evidence-based biological claims from standard nutritional marketing. To cut through the ambiguity, the food science community has adopted what we can call the Granado standard, a rigid baseline for determining true functional status. Under this standard, any health claim requires absolute validation through randomized, double-blind, placebo-controlled clinical trials. The trials must prove the food delivers potentially positive effects beyond basic nutrition at efficacious levels. However, it crosses a strict legal boundary if it claims to cure, heal, or prevent diseases. That remains the exclusive domain of medication. Upgrading a product from conventional to functional demands pharmacological-grade evidence. This exposes a massive engineering bottleneck, keeping bioactive ingredients intact from the factory floor all the way to the human cell. If extracting a known antioxidant is easy, why do these concentrated compounds consistently fail to deliver results in human trials? On the left, electron transfer occurs seamlessly in liquid. On the right, the compound hits a cell membrane and is actively rejected. Endogenous enzymes already manage cellular oxidation, so high-dose dietary antioxidants fail to decrease measurable oxidative damage because internal systems simply overwrite them. There is also a severe biological backlash. An overdose of dietary antioxidants can flip their behavior, initiating a pro-oxidant risk that causes deleterious cellular effects. Clinical evidence reveals that high antioxidant consumption during oncology chemotherapy treatments actually decreases the effectiveness of the medical intervention. These exogenous compounds create secondary metabolic disruptions as well. They have been shown to lower leptin levels. Leptin is critical for satiety regulation. Interfering with it blocks the signals that tell the brain you are full, directly triggering excess food intake. Simply dumping reactive phytochemicals into a product creates unpredictable physiological noise and potential harm. Extracting the active compound is only a fraction of the actual functional challenge. To see what successful matrix engineering looks like, we have to examine a functional model that actually works: phytosterols. Plant-based phytosterols share an identical structure with human cholesterol. In the intestinal tract, they compete for integration into dietary mixed micelles. Phytosterols achieve competitive inhibition, physically blocking cholesterol absorption. This yields the required clinical outcome, a measurable reduction in LDL cholesterol, lowering cardiovascular risk. The massive R&D bottleneck preventing this delivery is that phytosterols are highly hydrophobic and water-insoluble. To reach the micellar phase in the intestine, the physical formulation must be engineered to disperse the phytosterols into particles smaller than 25 micrometers. Failing this exact size constraint triggers two immediate consequences. First, it ruins the food product with a sandy mouthfeel. Second, the particles fail to incorporate into bile salts entirely. Overcoming this requires advanced particle engineering, specifically complex coacervation. Two distinct liquid phases rapidly mix, forming a protective polymer shell around the central phytosterol particle. Physiological efficacy is dictated entirely by this precise particle engineering. If the particle is too large, the intended health benefit simply passes through the body unabsorbed. The next major functional hurdle involves long-chain polyunsaturated fatty acids, specifically EPA and DHA. Human clinical trials confirm these specific lipids effectively reduce inflammation biomarkers and alter circulating lipid profiles. Their massive chemical vulnerability lies in their carbon skeletons, which contain multiple highly reactive double bonds. These bonds are rapidly attacked by three primary environmental variables before they ever reach a consumer: atmospheric oxygen, UV radiation, and high temperatures. Premature oxidation is catastrophic. It completely destroys the lipid's clinical efficacy while triggering severe sensory degradation in the final food product. Food technologists engineer physical shields. This spray-dried microcapsule uses a biopolymer shell to deflect external oxygen and UV rays away from the lipid payload. These barriers must be manufactured without the harsh temperatures or chemicals that would trigger the exact oxidative reactions they prevent. A functional compound has zero value if its delivery matrix degrades on the shelf. Physical stability is the absolute prerequisite to biological activity. True functional food design requires a strict R&D pipeline. Column 1 optimizes the physical extraction rate. Column 2 applies a protective encapsulation matrix, guaranteeing shelf stability and bioavailability. Finally, Column 3 demands randomized controlled trials to prove these engineering steps actually worked. A valid clinical trial must map the exact intake of the engineered food directly to specific measurable physiological markers, such as a targeted N3 index or reduced C-reactive proteins. This rigorous, multi-staged engineering pipeline stands in sharp contrast to the marketing illusion of simply stirring a raw extract into a conventional food product. The future of functional foods relies entirely on the precise, scaled engineering of micro-delivery systems capable of surviving the brutal journey from the factory floor into the human cell.